this is also, if that's later ignited, you can have a bloody, which is a boiling liquid expanding vapor explosion. So pretty nasty. Okay? So what happens? So how do we calculate how much will actually flash instantaneously into vapor? Well, the way we can look at it is that the energy difference, right, that this liquid has, its temperature is above its atmospheric boiling point. We can say that we have excess heat, right, in that liquid. And I'm not sure if this is, that this would be, Q is now heat, right, from thermo, not our QV, which was our ventilation rates. But that heat then is equal to, well, we can, is equal to this temperature difference, or is proportional to it. Now, this is a little bit, we'll look at that in a second. This is a little simplified, right? In this form, it assumes that Cp is constant. And that really depends on what your conditions, it depends on the liquid, vapor, right, that you're working with. But Cp, heat capacity, times the mass, of obviously heat capacity per unit mass, times the temperature difference. And in this, so Tb here is atmospheric boiling point. And T0 is our ambient. Or, most of the time what we're dealing with is that it's equal to the ambient temperature, right? But if to be perfectly clear, it's the temperature of the liquid, right? Before the flash. Okay, so we can see that this is an excess heat, right, that this liquid has, and the fraction that will vaporize then would be this divided by heat of vaporization. Sort of a simple way to look at it. So the fraction vaporized would be this Q, our heat, over our delta H vaporization. Okay, so that would be our MCP T0 minus TB over delta H. So now, of course, this was a little, yes?
So that seems to assume that Cp is constant over this temperature range. How valid is that for these super?
So the equation is exactly what I pointed out. This equation here assumes that Cp is constant. So this is highly simplified, right? So this is the fraction vaporized. No, this is mass. Actually, this is not the fraction. This is mass vaporized. Okay, so in this case, if we wanted to get the fraction vaporized, we would call it FV. It's NV over N, which is over there. It's equal to Cp T0 minus Cv over delta H. Okay, so as we pointed out, this is very simplified, right? So what we really are looking at, right, is dN, change in mass, right, the fraction vaporized, Cp delta H dt. CP is equal to A plus BT plus CT squared, and so on. So, right, to do this right, that's what you would have to do and integrate this, right? So you would integrate this from n equals m to n equals m with rest. And from T0 to T. So it all depends now. Yes.
Why are we integrating from m to n with
So we want the fraction basically. We want the fraction vaporized. So we're trying to figure out how much is actually vaporized. And we're going from at T0, all our mass is as liquid. Right? At TB we have some fraction.
Isn't that like at time 0?
Oh, sorry. Yeah, you're right. You're right. This is we want it. It's m minus f. Is that more clear? Sorry. Yes.
Oh, that's m minus.
N minus NB.
Okay.
So, so you know how to deal with that. That is roughly, because what we're dealing with, you would have to look up the heat of vaporization at ambient conditions, right? Where you're going. So that one we can say is constant. So this mass is constant. So this is a function of T. You can deal with that. If you're lucky, then CP is approximately equal to, right, where, how do you write it? No, that's the average. So you can calculate CP at, right, which is CP at T0 plus CP at TB over 2. And then you get, if you integrate that, you get the fraction of vapor is equal to 1/6 of minus average CP, delta HB T0 minus T. Okay, so, right, obviously that is significant, that's a little bit more complex than doing this. And the question is, right, how accurate are we? So let's look at an example to see what, what are the differences. And let's take one where we can actually get an accurate measurement. So your computer is on. So this is 416. We have our own hot water here, which contains 40 gallons of water. But because of a failure in the heat control, we continue to heat this until we rupture the tank. Okay? Because the pressure relief valve is clogged. Alright, so we reach the maximum pressure rating of the vessel and it ruptures. And it ruptures at 250 psi gauge. And we're asked to estimate the quantity of water flashed. Okay, that wasn't a whole lot of information. Right?
No.
No, so they're not giving us CP. Does anyone know CP for water?
1 calorie.
One what? Units are
1
key.
calorie.
4.182 joules per mole Kelvin.
What did you say? What did you say?
4.182.
4.182. All the information that we carry around and you're doing it. And that is 4. What did you say, joule per mole?
Joules per mole Kelvin?
No, I think it's joules per
Joules
gram
per
Kelvin.
kilogram in Kelvin, I think that unit is.
No, I think it's gram Celsius.
Hold on. It's kilograms per kilogram, joules per gram.
What's
You're
wrong
right.
with me? What happened?
Let me see.
You got
Oh, that's right, and this one I, actually don't have the, I don't have the number here because I decided to do it in British units. You know, when you get out in industry, you're gonna have to do British units, I'm sorry, I know it's just the way it is, you just, so we're gonna do every now and then, we're gonna actually do this in British units. You're gonna get used to BTUs instead of, joules. So I actually found, you know that Sandler, only has SI units for their steam tables, so I actually went and got the, steam tables in British units. So, but we have a hot water heater containing 40 gallons, so we need to know how much vaporize. Okay, all right, what do we know? So we know we need CP, okay, so we can look that up, at least an average value. We know an average value for water at ambient condition at least. So if you got this in thermo, what do you do? What does it look like?
Maximum work exposure.
Yeah, exposure.
Isotopic expansion. Does that ring a bell?
Yeah. Joule Thompson?
No, so you know, obviously that's an approximation too, but you know, we're just going from one pressure to another. So we can view this as an isotopic expansion, and then you can, from there, if you know that, right, the enthalpy is the same. Your starting enthalpy will be the same as your end point. Then you can calculate the fraction of liquid, right? We did that a lot in thermo. I know. At least if you, at least you should have.
Something like that.
If you had, I was gonna say, at least if you took thermo from me. So, but you know, let's see how that compares. So that would, using steam tables and doing isotopic expansion would be a little bit more accurate, right, than what we're about to do. So let's see what the differences are. So we have 40 gallons. Oops, 40, not 40. Okay, and it is at 250 psi gauge, it explodes. Okay, so you know we need fraction of vapor over M is equal to Cp Pc minus 2D over delta H. Okay. So what can you get from steam tables? And how?
You get the delta.
Yeah, so delta H, okay. Steam tables will give us delta H. Okay, so delta H, so here's right, if we look at delta H, we have
We don't know the final temperature yet.
Say it again?
We don't know the final temperature to find the delta H. One.
So what would be the final temperature?
You gotta do the delta S thing. Delta S is 0.
Delta H.
Well, there's too much going on now at the
Is it delta H?
right. So what do we need?
CP.
We need the final temperature. That is true, standard temperature and pressure. So, right, your hot water heater, you need right? How do we know what temperature the water was at when the thing ruptured?
Can you use the
Saturated, right. You have saturated water, okay? Saturated water, right? 250 PSI gauge. Now that was gauge pressure, okay, so that's 264.7 PSI absolute. Okay, if you go in and look at lookup values for that, we have to it's right, your table may not give you that. You might be able to find a graph where you can read it. If you interpolate, so you have P approximately 265 PSI, that gives T-sat, it's called T-sat, is equal to 406 Fahrenheit. And our delta H vaporization is 820.1 BTU per pound mass. British thermal unit. That's something that I promise you will hear. Okay, so and someone already said it's 1, so it's 4.118 joules per gram in degrees Celsius, or 1 calorie per gram in degrees Celsius. So CP H2O 4.18 is joules per degrees Celsius, or 1 calorie per gram in degrees Celsius. But if we just use, okay, wait a minute. Or, here's how we're going to choose. Okay, it's also equal to 1 British thermal unit per pound in degrees Fahrenheit. Right, the fewer conversions, the better. So the fraction vapor then is 1 BTU pound mass. I should write pound mass down here so you know. Degrees Fahrenheit. And we're going from 406 degrees Fahrenheit to what?
212.
212. It's the boiling point of water in Fahrenheit. Over our 820.1 BTU per pound. Okay, the units work out, so our fraction of vapor in that case is 0.1999. Okay, so about 20% is vaporized. So what's that? 20% of 40 gallons, 8 gallons?
Yes.
If we use this equation, which was the 1 minus exponent, right? Basically using this as an average instead of right? I think it turns out to 1.1. So I did 1.1 BTU times 406 minus 212. And then I actually looked at, where did the half come from? Oh, and then I averaged the heat of vaporization as well. It's 820.1